In this video, I'll introduce the voltage divider formula. This formula allows us to determine the voltage across any individual resistor in a series combination of resistors, if we know the total voltage across the series combination of resistors. Keep in mind that we're still applying KVL, KCL, and Ohm's law here. We're just combining them in one simple-to-use package. As we saw in the last video, a pair of resistors in series has the same resistance as a single resistor, whose resistance is the sum of the original resistances. Keep in mind that we're not necessarily changing our physical circuit. We're making a conceptual change which simplifies the analysis of the circuit by reducing the number of unknowns in the problem. Now let's determine the individual voltages across the resistors in our circuit. So we want to find V1 and V2 in this circuit. As we saw in the previous video, the current is the total voltage V over the equivalent resistance R1 plus R2. So by Ohm's law, V1 is equal to resistance times current, which is R1 times I. This resistance times the current through that resistor. I is equal to V over R1 plus R2. So V1 is equal to the total voltage V times R1 over R1 plus R2. So the voltage V1 is the total voltage V times its resistance over the sum of the two resistances, or the equivalent resistance of the circuit. Likewise, V2 is equal to R2 times I, which is going to be the total voltage V times R2 over R1 plus R2. So the voltage across V2 is the total voltage times its resistance over the total resistance. These two are voltage divider formulas. The voltage divider formula says that the total voltage across a set of series resistors is divided among the individual resistors. So if we have a pair of resistors in series in which we know the total voltage V, we can very easily determine the voltages across the individual resistors. The voltage V1 across resistor R1, for example, is simply the total voltage times the ratio of the resistor R1 to the total resistance. Another way to state this is that the ratio of any individual voltage to the total voltage is the same as the ratio of that individual resistance to the total resistance. So, for example, if R1 is 10% of the total resistance, then V1 will be 10% of the total voltage. Finally, before we do some examples on how to use our voltage divider formula, let's look at a general voltage divider formula. Suppose we have n resistors in series, R1, R2, on up to Rn. We want to find the voltage V sub k across the kth resistor Rk. So, by Ohm's law, Vk is equal to Rk times the current I. All of these are in series, so from our previous series resistance example, I is equal to the voltage Vs over the sum of the resistances. If I substitute this into this, I get Vk is equal to the total voltage, V sub s, times R sub k over the sum of the resistances, or the equivalent resistance of the entire circuit. So the ratio of V sub k to the total voltage is the same as the ratio of R sub k to the total series resistance. Now let's do a quick example. The circuit we'll use is shown here. We have a voltage source of 5 volts applied across a series combination of a 1 kilo ohm and a 2.2 kilo ohm resistor. We're going to measure the voltage across the 2.2 kilo ohm resistor. Our voltage divider formula says that the measured voltage, V out, will be the total voltage across the series combination, 5 volts, times this resistance, 2.2 kilo ohms, over the sum of the two resistances, 1 kilo ohm plus 2.2 kilo ohms. This turns out to be 5 volts times 2.2 over 3.2. Numerically, that turns out to be approximately 3.4 volts. Now let's wire up this circuit, make the measurement, and see if it matches our expectations. Here's my circuit. This is the 1 kilo ohm resistor. This is the 2.2 kilo ohm resistor. I'm using a digital multimeter to measure the voltage across the 2.2 kilo ohm resistor. Power is applied with the Analog Discovery's positive voltage supply. I'll turn on 5 volts now. So power is on. And we're measuring about 3.4 volts, which is what we expect from our analysis. Voltage dividers are also useful from a practical standpoint. For example, if we have a 6-volt battery, but we need to apply 3 volts to some circuit, a voltage divider is a simple way to implement this. We can take our 6-volt battery, a pair of series resistances, and we want to have 3 volts across, for example, this resistance. This voltage is half of this voltage, so this resistance should be half of the total resistance. So as long as we make these two resistors the same, we should get our 3 volts that we want. Now let's go wire this thing up and see if it actually works as we expect. I'm using this 6-volt lantern battery to apply 6 volts across here. I'm measuring my voltage across this resistor. I rather arbitrarily chose 2 1 kilo ohm resistors for my voltage divider. So long as these resistors are the same, I should get 3 volts here when I connect power. So let's connect our battery. And I get about my 3 volts. Using voltage divider formulas can simplify a circuit analysis considerably, since you're combining KVL, KCL, and Ohm's law into one equation. However, before you use a voltage divider formula, make sure that the resistors you're applying it to are actually in series. If you're in any doubt whatsoever about that, applying KCL at the node connecting the resistors can solve that. Next, we'll talk about parallel resistances and current dividers.